The reading assignment for this section is from Chapter 4 of Principles of Environmental Engineering and Science. It's the same textbook that I mentioned for population predictions, and I've posted the chapter on Lon Kappa, and it's in the supplemental reading folder. Okay, so let's start looking at and start talking about the different types of reactors. So, batch reactor. Can anyone think of a example of what is essentially a batch reactor that you have at home? It was a septic system, and let's think of a septic system. Septic system, we have a septic tank, and then we have a drain field, and we have flow in here, and basically the solids settle and the liquid flows into the drain field, and that liquid then infiltrates into the soil. We also have an HVAC system. So in HVAC system, we have, let's say, a furnace. We have outside air. We're going to heat that, and then we may recirculate some of that. So in both cases, we have flow in and we have flow out. So I wouldn't consider that a batch reactor because we have flow in and we have flow out. On the other hand, I'll get this tablet to work right. Let's think of a blender, an oven. Okay, an oven. We put the food in, we do something, there's some sort of a reaction that happens in it, and then we take it out. Okay, blender. We put the material in, we have some sort of a reaction, that reaction occurs, and then we take it out. Okay, washing machine. So basically think about a batch reactor as we have some sort of a system. You add whatever chemicals, and we can think about the blender making a smoothie. Okay, we add the ice cream, we add the strawberries, we add some ice. We then mix it well, and then during that period of time, some reaction occurs. In the case of a smoothie, it would be a physical reaction, but some change occurs, and we then take that material out in bulk. Okay, so in the case of a batch reactor, the concentration of whatever substance in the reactor is changing with time. So if you think about baking bread, during that period of time that it's in the oven, it's baking, it's changing. There's reaction occurring. Or even if we think about making bread and you make the dough and you sit the dough and let the dough rise. What's happening? The yeast is reproducing and CO2 is being produced. And then when it's risen, you can process it. So the concentration in the reactor is constant. So if we have a well-mixed system, then the concentration here versus the concentration here should all be the same. Now, we can also talk about a CSTR. Now, this gets into your septic system, which is not quite a CSTR, but we have flow in and out. So this is the big difference. So we can take the same sort of reactor that we had before. So that's our batch reactor. What makes it a CSTR is that we have flow in and we have flow out. Okay? And we have the concentration in the reactor. So we have a concentration in, we have a concentration out. If we have a completely mixed reactor, we can say that the concentration in the reactor is equal to what? Z out. Okay, so if we have a completely mixed reactor, then the concentration in the reactor is equal to the concentration leaving the reactor. If the volume is constant, that means that Q in is equal to Q out. And you'll often see an image like the one that I've shown you here to describe the reactor. We talk about an influent concentration, that's the flow in, and we talk about the effluent concentration, that is the flow leaving the reactor. So if we go back to the septic system, here, this would be our influent here. We actually have two effluents. We could say here that the effluent from the septic tank here is the influent into the drain field. And then we have an effluent here into the groundwater. These two terms are synonymous. So you'll see both continuously stirred tank reactors, you'll see completely mixed flow reactors. They're essentially the same thing. You can use those as synonymous. We can look at a lake, for instance, as a CSTR. It's a significant approximation, but we can. So what flows in? If we were to look at a lake like this as a CSTR, what are the flows that we have into the system? Okay, so we have rainfall, we have runoff, that surface runoff. We have let's say we have a river in, and maybe we have a river somewhere out. Any other outflows we would have? We might have pumping. Maybe we've got a water treatment system. Okay, we have evaporation. And we could have seepage. We also, if we had essentially a spring, we might have infiltration. So we could either have infiltration from the groundwater or we could have seepage into the groundwater. We would need to know something more. So if we're looking at a mass balance around this lake, we need to think of all of these factors. And we need, if we're doing a mass balance around some chemical in the lake, we need to think about how that chemical is actually entering the lake or leaving the lake. Now we can also have plug flow reactors. When you think of a plug flow reactor, think of that you've got some sort of a parcel of water that enters the reactor, and it's moving along the reactor. Within the parcel, it's completely mixed, and we'll assume no dispersion. Okay. So basically, everything that, here's our parcel of water that enters. So this is completely mixed. We have no mass entering that parcel, and we have no mass leaving that parcel. So essentially, it's kind of like a series of batch reactors moving down this reactor or pipe. Okay. So at time t, that parcel is here. At some time later, time t, it's over here. Some later time T3, it's here, and eventually it emerges. So the concentration of your chemical that you're looking at is the same whether you're looking at this point here, any point in the parcel. But the concentration at T1 is not necessarily, unless there's no reaction, is not the same as concentration at T2, which is not the same as concentration. Okay, so as long as we have a reactive chemical, the concentration in the parcel at each of the times will vary. So we can model a river. So back in 280, when you modeled the reaction kinetics in a river, what you used was Plugflow. So we can use the same model in a pipe. Same thing. We talk about a piping network. We talk about the distribution system. So for instance, if at the plant, so here's our treatment plan, we have a concentration of chlorine. We have a whole series of pipes. So we have a series, we may have hundreds of miles of pipes. So we can model that concentration of chlorine as that water moves through the pipe. And we can use these same sort of plug flow reactors. If you've used, or will use EPA net in 422, there's actually a component of EPA net that actually allows you to do this chlorine modeling. And it's all based on Plugflow. You could look at an HVAC system. You've got series of ductwork. And that ductwork can be then modeled as a Plugflow reactor. Now, as we talk about these systems, we will talk about the hydraulic detention time or the hydraulic retention time. Let me call it just the retention time. These are synonyms for the same term in the context of reactor theory. So for ideal conditions, the detention time, you'll see either the term T sub D or you'll see omega, and that is equal to the volume of the reactor divided by the flow rate. So we're going to make some assumptions in here. Basically, we're assuming we have a perfect reactor. So if this is our reactor here, we have flow in, we have flow out. We don't have, for instance, flow moving just in this direction and not, we want, really what we want is we want a circulation pattern like this so that the flow is actually throughout the entire reactor. So this would be short-circuited. We'll assume that we have no frictional losses. So we don't have rough surfaces that are changing the flow behavior. And we have no dead zones. So we don't have flow kind of sitting in, for instance, the omega. Okay, so it's just detention time. You see the term omega used, and this is volume over the flow rate. Does that answer the question? Okay, great. I apologize. Okay, the little image here is my attempt at showing you my first attempt at ever making a GIF. But what I was trying to show you in this is if you start here, and it moves a little bit too quickly, but if we start with pure water, so back in just a second, pure water, and then we start pumping in a dye solution, what we're going to see, and as you can imagine, is that the concentration of the dye in the reactor will increase over time. So if it's a blue dye, the color of this water is going to get darker and darker. And eventually, at some point, the concentration in the reactor is the same as the concentration entering the reactor, and the concentration leaving the reactor, in this case, because it's non-reactive, would be the same as what's entering the reactor. So if we start with and just plot the mass, in this case, the mass of dye in the reactor, we start here. So initially at time 0, we had pure water, and the concentration of, or the mass of dye in the reactor increases with time. And eventually it reaches some constant mass. So at this point here, the change in mass with respect to time is 0. So what we have here is this period of time where the change in the mass in the reactor is increasing. We have non-steady state conditions. And here, where the change in mass with respect to time is 0, or d mass dt is equal to 0, we have steady state conditions. So when we talk about steady state conditions, this is what we're talking about. The change in mass with respect to time is equal to 0. When we talk about C reactor equals C out, what condition are we talking about? Because this gets mixed up a lot. So when we're talking about steady state, change in mass with respect to time is equal to 0. When we're talking about when the concentration of the reactor is equal to the concentration leaving the reactor, what condition are we talking about? Exactly, a completely mixed reactor. Okay. I want to emphasize that because those two terms get confused a lot. So we can describe mass as the volume times the concentration. So the change in mass with respect to time is equal to the change in the volume times the concentration with respect to time, and we've got some sort of a rest of the equation. If the volume is constant, we can factor that out. Now we end up with change in concentration with respect to time, so we can plot concentration. So now we can plot concentration with time. The only time you can plot concentration as a function of time is when your volume is constant. Okay? So if you're plotting concentration with respect to time, you've automatically made that assumption that volume is constant. If that's not true, then you need to be plotting mass, not concentration, and you end up with a partial differential equation, and it becomes much more complicated, and we won't go there this semester. That's a ENE 802 problem. So let's look at a mass balance. Look at a simple one. And here we have a house. And we're going to look at consumer goods. We're not going to talk about food. So we'll talk about the food packaging. We will talk about if you bought a new TV, but basically anything that is non-edible. We have consumer goods entering. Some of that material ends up in the solid waste in the trash. Some of it may end up in the liquid waste. Some of it may be recycled. What we want to do is, the first thing we want to do is define the system boundary. So in this case, it's the house. The system boundary could be the subdivision. So we could look at a whole group of houses. The subdivision could be your own bedroom within an apartment. we can define, but we have to define the system boundary. The area, okay, the space within that system boundary is our control volume. So what we're looking at is the change in mass within that control volume. Now, if we go here, we can write now that we have an accumulation rate. So that's what we're looking at. We're looking at the change in mass in this space. So we can add terms. So we have the mass rate in minus the mass rate out, and that equals our accumulation rate, or the change in mass with respect to time. Okay. We can expand this, and we can write the mass of the consumer goods is what's in, minus the mass of the solid waste, minus the mass of the liquid waste, minus the mass of the recycled material, and that equals the change in mass with respect to time. If this equals 0, what condition do we have? So if the change in mass is equal to 0, what condition do we have? Exactly, steady state. So in that situation, we have a steady state condition. Now, I'm going to try the next